Hello and welcome back to Calculus 2, section 7.4. We're talking about trigonometric substitution.
Make an evil laugh.
Oh, actually I can make an evil laugh. But it's not time for that yet. We're going to open the gates of hell later. And that's when the evil laugh is coming up. Right now, this is still enjoyable to some point for most. Trigonometric substitution. We are going to take a look at a problem that has no trig in it, transform into trig domain, and solve the problem using the trigonometric integrals, and then bring it back into x. If you are lucky to have a definite integral, you can transform the limits from x into theta, and then you don't have to go back to x domain. Don't forget plus c again for all indefinite integrals. Now, I'm going to teach this section differently than what the book does 100%, because the textbook is asking you to memorize 3 formulas, recognize which situation it is, and then use the appropriate formula. And then technically, when you are supposed to go back from the trig domain into x domain, it's technically good luck at that point. Book tells you good luck, and then hopefully you get it. The way I like to do this section is I have one method that outlines all 3 possibilities, and as long as you are able to set up a trigonometric function from a triangle, you will be able to solve all of the problems equally in the same fashion, and I would like to say simply. Now, if you don't find the method that I show interesting, this is the disclaimer, right? The fine print. You are welcome to learn the 3 formulas from the textbook and then just plug those in and hope it works out at the end of the problem. So what I'm going to do here is I'm going to remind you that when you have a right triangle, you have 3 sides, where the longest side is called the hypotenuse, and you have 2 other sides which are each called legs. And then you can write the a squared plus b squared is equal to c squared, which is the Pythagorean theorem. So from here, you can write that c is equal to square root of a squared plus b squared. You can write that a is equal to square root of c squared minus b squared, and b is equal to c squared minus a squared. Now, this is all not even, it's pre-algebra, or whatever it is, algebra, when you learn the Pythagorean theorem. Now, I want you to observe these formulas and recognize that if you have a plus, then these 2 are legs, and if you have a minus, the first one is the hypotenuse. That's how you know what to pick from the integral to put on each side of the triangle. That's how it works. The first formula, there is a plus, and these 2 are legs. Yeah. The second 2 formulas is a minus, and the first one is hypotenuse. Now, this is how, we'll see how that plays the role when we take a look at the first example. So say your first example is square root of 16 minus x squared dx. That's it. We see that we can't do anything with this. It's not a basic integral. It's not a u sub because there is no x in front of the square root. The u sub will most likely not work. I don't think it's going to work because you can differentiate square root, you're going to get something terrible, and then later you have to integrate. So I don't think u sub works either. By parts, I mean. So we should look for the new method. And this is what I do. When I see a problem which has this difference of squares, you can set up a triangle with the angle theta in one of the corners. And then I go and I say, I have a minus sign, which means that the 16 is a c squared, which means number 4 goes on the hypotenuse. Did that make sense?
One half if I make it b or a.
You can't, because if you look at the formulas here, this is what I was telling you earlier. If there's a minus under the square root, c is the first, and that's 16 in this case. This could have been x squared minus 16, then x would have to go there. Now, because these formulas are symmetric, you are allowed to put x on any of the two, and by Pythagorean theorem, the third side will be this. So if you are able, not if, but when you figure out how this works, you will see how systematic this is to solve every single problem without memorizing anything. And to make the matters much better than what the book offers is that this method here gives you a triangle, so when you end up with the trig solutions, you can look at the triangle and convert them back to x's. The method that they give you in the book, memorizing 3 formulas, you don't have the triangle. So if you end up with a function, with a trig function, that you need to go back into x, apart from the original conversion that you used, you have to do a ton of trig identities to make it work, which is not, in my opinion, not as cool as just looking at the triangle and know exactly what the answer is. So your goal is to figure out these formulas you already know. So you look first whether you have plus or minus under the root. If it's plus, square roots of each of these guys are legs. If it's a minus, the first one is hypotenuse, and then it really doesn't matter where you put the other one, because it's one of the legs. And here is the big thing that you need to remember. You will write your trigonometric functions towards the number. So one of the 3 sides will be a number, like in this case is 4. One of the 3 sides will always be a number. Make sure you use that side in a conjunction with other 2 sides to create your trig functions. From there, everything else is automatic and straightforward. So I have x and 4. That would be opposite and hypotenuse, which is sine. So sine theta is x over 4. This means that x is 4 sine theta, and dx, when you differentiate, is 4 cosine theta d theta. So one of these will always give you x, and you immediately differentiate, because you know the substitution method, you have to substitute x and you have to substitute dx, right? With du. In this case, you're substituting dx with d theta. To get the second circle, so this is the, you know what, I'm going to color code them. So this was a purple one, and the second one will be the green one. The green one is going to give us cosine theta, which is the square root of 16 minus x squared over 4, from where the square root of 16 minus x squared is equal to 4 cosine theta. So you will always have this situation. This will be the same for every problem. You will look at the problem, create a triangle, and then write 2 trigonometric functions. Now, the pairing will either be sine with cosine, secant with tangent, and cosecant with cotangent. It will never go anywhere else, because it cannot. Mathematically, it cannot. Those are the pairs. So you will see, we'll do a lot of examples of this, so it will become automatic. Now look at this. You have blocks. You know, when mechanics today, they don't fix cars. They just swap parts, right? They used to actually fix the part, right? It was cool. Now it's just take the unit and just swap it with a new one. So that's exactly what you're doing here. You take out the square root unit, and you put what the square root is equal to, so 4 cosine theta goes instead of that. You take a unit of x dx, and you put what dx is for. You are not going to use this, or that in this particular problem. So you just look at the components you need to replace, and you find them somewhere in your equation. Again, you will get basic trig functions, and you will solve them for x or for whatever feature they have. And when you solve them for those features, sometimes you're going to use all 3, sometimes you're going to use only 2 of them. So in this case, I'm going to yank out the square root, and I will put 4 cosine theta. I'm going to take the dx out and put this instead. So looking at the formulas, I have integral of the square root, which is 4 cosine theta. And then instead of dx, I have another 4 cosine theta d theta. So this is 16 integral of cosine squared theta d theta. How do we solve this integral? Power reducing. You must know power reducing. So that's going to be power reducing is over 2, which means 16 divided by 2 is 8. 1 plus cosine 2 theta d theta, which is 8 times theta plus sine 2 theta over 2 plus c. We're done, right? Yes.
When you go from x equals 4 sine x to dx equals 4 cosine theta, I know you're just integrating, but what? How do you know? How do you add the d theta at the end? Is that just
this d theta? This d theta is this d theta here.
Same way you would
It's the same thing as Utah. So if you here, so the green goes with green, and the pink goes with pink, because this.
Yeah. Okay. So you're just deriving the 4 sine theta.
So now we have to go back. Now, if you get something like this with a textbook, because all you have is this. The textbook will only give you this one equation to try to solve everything. I don't have to worry about that now.
With the 4 cosine theta, how did you do it twice, even though, did you do the same substitution?
I just underlined it. You didn't pay attention, huh? Look, this guy is this guy from here. I just did this.
Okay, let's do it.
This one, and that one. Right?
Yep.
Good. The last part of this problem is to go back and put back everything back into x. Now I have this term over here that's sine 2 theta, so I have to use identity to expand that. So a theta plus 8 sine theta cosine theta plus c. This was using the identity, right, for sine 2x, which is 2 sine x cosine x. And now all I need to do is to read what these things are up there. Theta. I can get theta using inverse on any of these. So sine inverse x over 4. Plus 8 times. I'll explain this from scratch. Look, sine theta is given as x over 4. And the cosine theta is given as square root over 4. And now we simplify. Now obviously all of these results have to look like this, because this is what the section is all about. I have a half there, 2, so half x plus C. Fun answer, right? So how did I get this n? You all followed up to integrate, and we have that as the answer in terms of theta. Now we have to go back into x. I see the 2 theta here, which means that I'm using the double angle formula, and I'm writing it right there. So now I need to replace each one of these building blocks with their equivalent x domain functions. Theta. Theta can be expressed as either I can solve for theta here, or I can solve for theta there, whatever. Theta, on the first equation, I have to apply inverse sine on both sides to get theta alone. On the second equation, I have to apply inverse cosine. You pick whatever one you want. So I applied inverse sine here on both sides. So theta is equal to inverse sine x over 4. I had 8 in front, so that's that term. The next 2 terms are much easier because sine theta and cosine theta are listed what they're equal to as our basic functions. So I'm just, again, replacing the entire sine theta with x over 4, and I'm replacing cosine theta with the square root over 4. So those are just easy replacements. This was the only one that you actually had to do a little bit of work. And once you have that line, you go to the lower line here and just write everything simplified, right? 8 cancels 4, and then 2 cancels 4, so you get 1/2 x, so on. Now, as a student, I said this many times, I used to love integration because I can always differentiate and check my answer. So you should be able to take the derivative of this expression, and you must get the problem you started from. If you're not getting it, presumably that you did all the algebra correctly, then something is wrong. It has to be. Because the way to check this is to take the derivative, and if you get this, it's right. If you don't get it, it's wrong. So clearly we only had a chance to do 1 example, so we'll do another 5 or so, 6 examples. They will all have the same setup. If you go and watch this video over and over again, you might be able to just learn it that quickly to solve as much homework possible. Yes?
I have a question about the data. Obviously, you can't put it at the right angle because that obviously but the other 2 sides, the other 2 corners, does that
No, because you can pick theta in the other corner as well, which will just swap equations. So the first, if I pick theta to be at the other angle, then this will be cosine, this will be sine. That will propagate to the problem, and the problem will look completely flipped. But remember that sines and cosines have the Pythagorean identity that connects them with the number 1, and I can always take number 1 out of plus c. So all of those answers are actually, they look different, which creating that nightmare for me, but they all look, but they're all equivalent, they're all the same. Mathematically, they're all the same. So I will see you all on Monday. Do a lot of work.